Morning, everybody. It's my pleasure and an honor for me to introduce Professor James Binney, who's going to give today's seminar. If I was to go through James's entire illustrious biography, would be here at the end of the seminar. Let me just mention that he is a recipient of awards associated with names like Dirac and Maxwell, and most recently Newton. He's been for many decades a world authority on galactic dynamics, and he literally wrote a book on the subject, and a book on galactic astronomy, and a book on quantum mechanics, and a book on condensed matter physics, and recently popular science books on astrophysics and on entropy, which is one that's about to come out. He is also an inspirational teacher, both to me and to many other people at the best college in Oxford. And today he's going to tell us about the normal modes of stellar systems. So please take it away, James.
Thanks, Chris. Well, it's a pleasure and an honor to be back here. I have many happy memories of the Institute for Advanced Study, but they are 40 years old. So here's a refresher. Right, okay. So this is my agenda. I'll talk briefly about the astronomical context of what I'm going to say very briefly. Then I'll just remind this audience of what I'm sure doesn't need reminding of, which is the importance of normal modes in physics. And then I'll go slightly more slowly, I hope, through linearized stellar dynamics, so you can see how it works in that context. And then I'll introduce the normal modes of these systems and talk about three applications of them. Okay, so the astronomical context is, I would say that we've got to a point observationally where we are able to resolve fine structure in galaxies, disequilibrium, which is on the whole minor, but interesting. And in order to, the natural way to understand that is through through perturbation theory. These few figures we've heard about a good deal this week. The Gaia spiral discovered in the DR2 data in 2018, and these are other manifestations of them. Similar things are seen now in other galaxies because instruments like MUSE get three-dimensional representations of other galaxies now at very high very significant spatial resolution. So these are the sorts of things that we need to shift to. Also, we expect, I think we should expect large-scale distortions of galaxies. Here's a famous galaxy M101, which shows clearly that the outer part is not centered on the inner part. And is this part of an oscillation of the inner part with respect to the outer part? One would like to know, one would like to understand how that plays out and what we can learn about the matter which we believe exists in this larger volume in large quantities from studying this kind of offset. So I think the new frontier in stellar dynamics is fluctuations around equilibrium. I was sounding off yesterday at my complaint that we still don't actually have adequate models of the equilibrium that we would perturb, but the name of the game is clearly get good models of equilibrium, the best model you can, the closest representation of the data that you can with the equilibrium model, and then perturb it and see what happens next. Okay. So in physics, you've got some system of dynamical equations. What do? You find an equilibrium solution, you linearize around that solution, and you assume that, that every perturbed quantity goes like this, and you're kind of guaranteed that there's going to be a set of solutions like that from the time translation invariance of physics. The universe is not time translation invariant because of the Big Bang, but physics exists before the universe. It is time translation invariant. We insist. Okay, so and examples. Well, the standard model of particle physics. I mean, there's some complicated Lagrangian for the vacuum. The normal modes are found of it, and the normal modes go by these sorts of names, right? Condensed matter physics. You make some continuum model of you go from the discrete to the continuous, usually model of your crystal, and you consider excitations of those, and they go with those kinds of names. The magnetohydrodynamics, other kinds of waves, exactly the same phenomenon. You've got some system of equations, you linearize around them, and you identify what the different normal modes are, and they tend to get names. And these names are so successful. I mean, this process is so successful that the linearization provides the language by which we understand material reality. It isn't just a computational tool, it's a conceptual tool of the first importance. We think of electrons, photons, etc., as being real, but actually we know they're not real. They're actually just ripples in this mysterious space-time continuum. They can be at some level, well, we can understand them, we can approximate them, we can describe them using these abstract things, these normal modes. And we think of mode-mode couplings as interactions between these particles, et cetera, et cetera, et cetera. That is our conceptual model of material reality. Okay, now the key properties of normal modes that make them so useful, I think, are these two. First, their energy is additive. Energy is a quadratic quantity, so generally the energy of solution A plus solution B is not equal to the sum of the energies of the solutions, but for normal modes, as we teach every first-year class, it is. It's a special property of normal modes, which obviously plays a very important role in our use of normal modes, make our conceptual picture. I've got an electron, I've got another electron, I've got two electrons, and therefore I've got 2 units of mass, not 2.1 something or other, or 2 or 1.95 or something. Second, they're a complete set of solutions. In other words, in principle, you can cobble together any solution of your system by adding up these normal modes. And the thing the crucial point that we seem somehow to neglect is that the things that people for generations have called the modes of collisionless systems don't have these properties. Okay, so let me introduce you to the normal modes of stellar systems, to do which, of course, I need to start by talking about the linearized stellar dynamics. So as in condensed matter physics, we're going to replace the discrete. We're going to start by replacing a galaxy or a cluster made of discrete blobs of mass by a continuum. We will, as in condensed matter physics, we can go back and include discreteness later, as how it modifies this continuum. So we've got a distribution function f here. This is the one particle distribution function, which is a function on 6-dimensional phase space, and gives you something like the probability of finding any particular particle at probability density of finding it at some location in phase space. And it satisfies the equation that df by dt is equal to the Poisson bracket of the Hamiltonian, which I write down here, and the distribution function. And when we linearize, we express f as f0 plus f1, where f1 is presumed small with respect to f0. And this is a linear structure, of course, the Poisson bracket. So we expand it, we get these terms. And then we cancel this term on one of the terms over there, this term, right, the 0th order term, and we're left with this linearized equation. And as I say, the Hamiltonian, well, I call it a Hamiltonian, we call it a Hamiltonian, but it is actually the Hamiltonian per unit mass. So it's 1 over mass of p squared over 2m plus the potential energy v, which is m phi, et cetera, et cetera. And h1 is nothing, the h1 up here is nothing but phi 1, the change in the potential energy of the system, because the kinetic part doesn't change, it's always p squared over 2m. And the other thing we have to bear in mind is Poisson's equation, which tells us that the change in the potential is 4 pi g times the density, and the density is the integral over velocity of the change in the distribution function. Okay, now we operate with angle action coordinates in solving this equation. So these are just special coordinates in phase space, such that the momenta, called actions, are constants of motion, and that implies that the conjugate variables, called the angles, increase linearly in time. And when we write, so they are canonical coordinates, theta and j are canonical coordinates with all the nice properties that x and p have. And when we write the collisionless Boltzmann equation in angle action coordinates, becomes this. So the Poisson bracket can be expanded into df by dj, df by d theta, dh by dj, minus df by dj, dh by d theta. And so these two bits are just the Poisson bracket, because omega, the frequency, is just the is just the gradient of the unperturbed distribution function. So this is just the collisionless Boltzmann equation written in terms of angle action coordinates, which is made easy by the fact that angle action coordinates are canonical things. And then we expand our perturbed potential we Fourier expand it in the angle variables, because the real space coordinates are phase space is periodic with period 2 pi in these angle variables. So this Fourier expansion is guaranteed. And similarly, we Fourier expand our distribution function. And then obviously we can work out what these df by d thetas are, because we can explicitly differentiate this, and we get this equation that every coefficient fk in here satisfies this simple linear equation. Right. So let's talk about the what's the energy of a disturbance? Obviously, that plays an important role in any perturbative theory. To figure this out, we create the disturbed distribution function by yanking on our system using an externally applied potential phi e. It's kind of a material point that you can't create any old disturbance by doing this, and therefore, and that means that the disturbances we need to consider are somewhat restricted, because you can only maneuver your system by pulling on it with the only means at your disposal, which is applying an external potential. So the rate at which you work, so this is exactly analogous to what you do in a second year electromagnetics course when you're telling the students about pointing vectors, etc. You want to know what the energy is that's stored in the Emag field, so you create an Emag field by dragging charges through space and figuring out how much work you have to do that. So the rate at which you work with this potential is the force that you're applying, which is the gradient of the potential times the mass, times the velocity with which you're doing it. And of course, you're doing it at every location in space, so you better integrate over space. And this d cubed x and that d cubed v can be, and there's a d cubed v involved here, can be combined together so that it becomes this, where d6w simply means the integral over all phase space, right? Just of this product here. And a totally straightforward manipulation allows you to take this integral and break it down by expressing everything in terms of f becomes the sum of fk e to the ik theta. We can break this down into and show that this is the sum of derivatives. It's a dk by dt. This could be written as dk by dt plus dp by dt, where k is this strange object, and p is this. P is obviously the potential energy of the system, because one of these integrals will give you the potential at x caused by all the masses at x primed, and then if you integrate the density at x times the potential at x, you get twice the work done, the work needs to be done to disassemble the system. So that's, oh, well, sorry, it keeps happening. So that's clearly the potential energy, and that means that this rather obscure statement has to be the kinetic energy.
Can I ask,
Yeah.
these kinetic and potential energy are second order in fluctuations.
Yes.
So second order F naught also changes, but that's neglected in linear theory. It's never clear to me whether we have to worry about that. In what situations we don't need to worry about that.
Yeah, interesting point. Let's discuss it later. I haven't got anything intelligent to say immediately. So to handle Poisson's equation, the standard procedure in this field is to use bi-orthonormal potential density pairs. That's to say a set of functions, rho alpha enumerates the functions, and phi alpha, which have the property that they're mutually, that phi alpha is the potential which is generated by the mass distribution rho alpha. And they also have this important property. So that if you multiply rho alpha by rho alpha primed by phi alpha star, the complex conjugate of this, and integrate over space, you get nothing unless alpha equals alpha primed. And this is, when alpha is alpha primed, this is essentially twice the potential energy associated with the density distribution rho alpha. So this thing, let's hold it differently. This thing clearly has the dimensions of energy. So this constant in here is constant of our choice. It's at our disposal because we are free to normalize these any which way we want. And clearly, if you increase the normalization of this, you'll increase the normalization of that, and you'll increase the normalization of this by the square of whatever you chose originally. So the minus sign is there because this is clearly negative because it's a potential energy, and the curly E is there because we need a normalization constant with the dimensions of energy. It's very common not to put in this curly E thing in this field. I find that deeply confusing because I hate to have something which has dimensions of energy equal to something that is dimensionless. Okay, so we use these things to solve Poisson's equation, the solution procedure being absolutely straightforward. If I have a density distribution rho, I expand it in terms of these basis functions, which I can easily do because I can find the expansion coefficient simply by multiplying my density distribution by the appropriate phi star and integrating and dividing by this and whatnot. Having done this expansion, I have immediately what the potential energy is because I just have to add A alpha times the appropriate basis functions. So this is a powerful way of proceeding, and a relationship that's very useful to have in your brain is this expression. So this is the Green's function of Poisson's integral, clearly, and it's very easy to infer from these statements. If you say what phi is, replace A with this, you will soon see that you get an integral over space of something times rho. And we know from Poisson's integral that that something should be this, and therefore that something, which is this here, sum of products, must be this. So you get a representation of the Green's function of Poisson's equation using these basis functions here. That again there are many analogues in many other branches of physics. This is all very ordinary. Okay, so a relationship that's worth bearing in mind is in order to find A alpha given not rho, but given the perturbed distribution function, well, then we have to integrate. To get rho, we would integrate d cubed v of the perturbed distribution function, and then to get A, we would multiply d cubed x of phi star, etc. So this integral is clearly A. And if we write everything in terms of, if we expand this in terms of angle action coordinates, that's phi expanded in angle action coordinates. And if you then expand this in angle action coordinates, we get this. And by the beauty of canonical coordinates, this, which was previously d cubed x, d cubed v, can be written as d cubed j, d cubed theta, because that's a property of any switching canonical coordinates. And now we can work out the integral of d cubed theta, and obviously we get 2 pi cubed delta whatever, and then we can do and then we wind up with this expression here. So anyway, that's a relationship that we often need. And if we ask ourselves what the potential energy is that is associated with a density distribution rho and its associated potential, that's this, then yeah. And then phi, of course, is real, so I can take the star at no cost to myself, and then we can expand everything and do the integrals, and you wind up with this expression here, which is telling you that the potential energy is proportional to the sum of the squares of the expansion coefficients. And there's a sort of analog here. If you would ask what the electrostatic energy is, it would be the sum of minus a half sum E squared with the electric vector. So there's a sort of analogy between these expansion coefficients and the electric energy, the electric field of an electrostatic problem. Anyway, we can now write the energy. So this is the energy of any disturbance. This is the kinetic part, and this now is the potential part rewritten. We will want. Okay. So now finally we get to normal modes. So to move to normal modes, we of course make the time dependence e to the minus I omega t. That's what one does. And so we plug that into the collisionless Boltzmann equation, which we already saw. That had a df by dt. That df by dt becomes a minus I omega t. We had a d by d theta, which became ik dot omega, where omega is dh by dj. So we can cancel various i's, and we have this relationship. This is the equation that has to be satisfied by the expansion coefficients of a normal mode. Now, this looks very much like the standard normal mode type thing, because you might say phi k depends on fk. Well, it jolly well does depend on fk, but it depends on all of the f's at all. And this thing here, that's a function of j. I've suppressed the, so it's f is the sum fk of j e to the ik theta, because f, of course, is a function of theta and j. So this depends on j, that depends on j. So, but this phi depends on every k and every j, right? So if you want to figure out what phi k is, you have to sum over all the fk's and integrate over them. So it involves an integral dj and some k. That means the dependence of this thing on f, any individual fk, is infinitesimal. So you can, if you change this, you essentially don't change that. That means that we should regard this as a known quantity, and this equation, what this equation is telling me is that this multiple of fk is equal to this on the right-hand side. If this multiple vanishes, then this equation doesn't constrain fk. There's nothing to say about fk. So the solution to this equation, as Van Kampen pointed out in 1955 or something, in the plasma context, a slightly different, same equation in a different, somewhat simpler context, the solution to this equation is that fk is equal to this thing divided by this thing whenever this thing is non-zero. That's what the p here stands for. It's sort of by analogy with the counting principal part. So it's equal to this on the proviso that we exclude points where k dot omega is equal to omega, right? And then when this vanishes, there's no constraint from here on fk, so we should add an arbitrary function times a condition that says it matters only when we are at those special points where k dot big omega is equal to omega.
James?
Yes?
In these kinds of problems, sorry to interrupt.
Yeah.
There's often a subtlety when you take a Cauchy principle apart, or whether you let omega go to omega minus I epsilon is the normal mode that has been infinitesimally small. But so is that always the case? That
Yeah, because what we're not going to be allowing omega to become complex. We're arguing that omega is a real quantity.
yeah, but
Omega, and
minus I
we're
epsilon
simply
is
excluding
epsilon.
that point here, and we're asking what is the normal mode of real frequency omega? Here it is. And the point that Van Kampen makes is that you can do this for any real value, right? And you get what you get. Let's investigate what the properties of that is, or what the properties of that are. So this is an arbitrary function that's really important. Okay. Now, if we consider the places where that swings in, so it's completely irrelevant what this is. Obviously, it doesn't matter what you choose for k dot j at points where omega, where k dot omega of j is not equal to little omega, right? Because it plays no role. So let's consider the set of points where k dot big omega is equal to omega. That's clearly essentially a two-dimensional continuum of points because this is one constraint on three actions. The frequencies vary with the three actions.
Does GK even have to be smooth? Just any
Does who have to be smooth?
Does GK, the function, even have to be a smooth?
No, I don't. I shouldn't think it is. I think it's completely in our pocket. In fact, I will be arguing that we should make it not smooth. Or sorry, it's helpful to think about it when it's not smooth. Okay, so the point is, where are we? Yeah, we have, well, right. At any frequency, we have a two-dimensional continuum of modes obtained by different choices of this. And also, we can play this game at any frequency. So we have massive degeneracy. But we haven't finished, we're not done because we have to respect that there is a relationship between the fk and the phi k. I said that phi k we can consider known when solving the equation for fk, but of course, if you know all the fk's, that specifies phi k by Poisson's equation. And to find out what that relationship is, we take the equation we just had, which was fk is equal to this rubbish, with plus gk times that. We multiply by alpha prime star e to the ik theta and integrate overall phase space. Obviously, we're entitled to do it if we want to. And after a little bit of algebra, so this d6w we're going to break down into d cubed theta, d cubed j. You can imagine that some of the theta integrals we can do and so on and so forth. After some algebra that's not at all deep, we come to the conclusion that this is the equation that we get. Good. We've integrated away the e to the ik theta, and that has turned this from being the whole function into just its k basis. So this is one of our basis functions projected into angle action space. It's the kth component of it, and that's happened because we did the integral over theta of this crap times fk. Similar things happen over here, and now the equation that if we now sum over overall, take this and now sum over all k, then this will become A alpha, essentially A alpha, from a formula I showed you already. And here, oh, bother, sorry, and it will come, no. Yes, I'm in the right page now, Lars. And this is going to become, so there's an A alpha over here, we're going to have an A alpha over here. So we're going to have, after we've cleaned up some constants, this is going to be A alpha. We're going to have a matrix, namely this matrix, times A, that's that A, on the right-hand side, and this sum is the sum that's implicit in that matrix dot A. And then here, we're going to have what I'm calling G. It is just what you see it to be, right? Now, this G is actually, what this is the expansion coefficients in terms of our basis functions of the mass distribution that is produced by this part of the distribution function. So it's a very physical thing. So what this equation says is, well, maybe we want to go over the page. No, we're not going to do that now. We're going to, okay. So this is just algebra that we've derived this relationship between G, which sort of drives the mode, and through your choice of G sub K, of the G sub Ks, and the A's, which are the expansion coefficients of either the density or the potential, you can think of it either way you like, of the response that you get. the perturbed distribution function that emerges from your driving. So let's consider a very simple example to get to fix ideas. So let's choose g of k to be a delta function. So that's saying g is going to be nothing unless j is equal to j naught. So j naught is picking out one orbit. So we're going to say we're going to consider the normal mode, which is driven by one orbit, j0. And what the mode is going to be a combination of the density produced by this orbit and the gravitational field, and the density distribution by all the other stars in the system. So when gravity is present, this orbit is going to produce a sinusoidally varying gravitational field. That sinusoidally varying gravitational field will drive steady oscillations in the other stars as driven oscillators, and those driven oscillators will generate a density field that's described by the A's. If we consider, to keep things as simple as ever possible, let's consider the unperturbed system to be a razor-thin axisymmetric disk. When K now becomes, I'm sorry, should be a curly L, but I'm thinking Microsoft wouldn't deliver one. Right, so imagine that's a curly L and M. So K in this two-dimensional system will have just two integers, L and M. And it's very straightforward to show that the surface density, which is what the three-dimensional density becomes in the disk case, looks like this, caused by that. So first of all, it has simple e to the im phi dependence. That's a consequence of the way that the angle action coordinates work when your underlying system is axisymmetric. It's a consequence of irreducible representations, if you like to think in terms of group theory. So we're getting a mode in the conventional sense of it's an e to the im phi structure now. Otherwise, we've got a certain integral here of this stuff. So this is the radial angle variable, and here we have some function of the radial angle variable, which depends somewhat on the potential. And this stuff gets integrated, and on the bottom there's this interesting thing, which is the partial derivative of the radius is going to be a function of angular momentum and theta r, and this thing is going to vanish, dr by d theta r, at pericenter and apocenter. So this term is telling you that there's going to be an enhancement of density at the turning points, pericenter and apocenter, and this is going to provide some kind of structure within that. So if we consider the bare modes, so when we switch off gravity, we just ask what is the density distribution that's produced by G with no self-gravity considered, then the density distribution is confined between pericenter and apocenter. This is the mode L equals -1, M equals 2, L equals 0, M equals 2, L equals 1, M equals 2. And what you see, is there's enhanced density around the edges, and you kind of have alternating here. The density is very high here. In this mode, it's very low there, but high here, where here it's low, etc., etc., etc. So you just have a pattern like this, and you need to this pattern is times e to the I omega t. So you should imagine it as oscillating in time. And oscillating in time, it's going to generate a gravitational field, which is going to drive the nearby stars and cause there to be density changes inside the torus and outside the annulus. All right, so we're back to this equation here. We had that A is MA plus G. which we can rearrange to A is 1 minus m to the minus 1 times g. We think of MA as the dressing. If there's no gravity, m is 0, and the density coefficients associated with the whole mode are simply the density coefficients associated with the driver. MA is the contribution of dressing. So that's non-resonant stars which are responding to the driver by the resonant object. So maybe I need to say that differently. And again, with G of K, what we have done is taken an orbital torus and populated it with stars in a non-uniform way. So that's because K is non-zero. So then this non-uniform distribution of stars is creating a density distribution which oscillates sinusoidally forever. And then the rest of the system responds to that sinusoidal oscillation. And we have taken we are considering the very special case where there's just one torus on which we put this non-uniform distribution of stars. Right. That's what I was doing before. So clearly A diverges if M is able to get close to the identity operator. And clearly if the determinant of M minus 1 is small at some frequency omega, then it's reasonable from the properties of holomorphic functions to imagine that to predict that it is going to vanish either above or below the real line. So we're on the real line here, and in this zone here, where the dressing is large, that's what I'm implying by the blobbiness. It's large because M is close to the identity, that is to say, 1 minus M is close to 0. So if we go a small distance, holomorphic functions tend to drift towards their next singularity. So this thing so it's reasonable to expect that close to this line, there is a point in the complex frequency plane where M 1 minus M is a singular matrix. And that is a Landau pole.
But you're strictly restricted to real omega because
Yeah, you're coming back to my point.
Yeah, so the real modes are real omega. But if you just want to ask yourself, what is the mathematical structure of this object here, you're free to think about it in the complex plane. It's helpful to think about it in the complex plane. And if this thing is small somewhere on the real line, it implies it's extremely likely that it damn well vanishes somewhere near to the real line. And I'm saying that is what we're all familiar with. That is what a Landau pole is. We'll talk a bit more about that.
Can I ask a question, James?
Yeah, please.
I'm trying to understand in at least the problems that I'm used to dealing with. Usually, showing an eigenvalue problem, and usually you find first the frequency, and then you find the eigenmode associated with that frequency. If I understood correctly, in the previous slide, you were already talking about an eigenmode, but you do not know yet.
There is no dispersion relation. I should have said that. Sorry. That was the point. That in the let's go back to the right place. Yeah. So if this were, for example, Fk, then I could put everything on the left-hand side, and I could say some operator times Fk is nothing. And then of course, it means that operator has to be singular, and that gives you your dispersion relation. We don't get a dispersion relation because we got this thing on the right-hand side, which isn't just functionally.
So if I may ask, how do you know you actually have a mode without knowing yet at what frequency is going to oscillate?
Because a mode is just, I found solutions which do oscillate e to the minus I omega t. That is a mode. The spectrum is continuous. This is a fundamental difference from these other fields. Much follows from that, but they are the modes.
So the arbitrary function gk what if like there has to be some other constraint which actually fixes GK as in case's original paper, right? And he uses another constraint equation to fix.
No, he doesn't really fit. Well, the other equation is this one that it is this relationship here. It is the thing, it's the thing that specifies the mode, right? So the degeneracy, it has to be stressed, is absolutely horrendous. It's not quite every frequency which is within the range that K dot omega, we got some unperturbed Hamiltonian, which means we've got some function omega given us. And then K dot omega for a given K can cover some range. It may be that it can't cover the whole real line, but it can cover a huge part of it. And at every such frequency, we can find many normal modes. So we have a continuum of frequencies, and at each frequency, we get to choose G, and so we have a wide range of normal modes. Right, now consequences of this continuity, of this cornucopia of normal modes. Well, the continuous spectrum actually is the main thing. You can't excite any individual mode. If you walk up to a machine, if you walk up to a bell and knock it in the right way, or a piano string, you can excite one normal mode because they have discrete frequencies, and you can make sure you hit only one of them. You can't do that in a stellar system. You always will excite modes that cover a range of frequencies because of this continuity condition. Because the phases increment at different rates, obviously, because omega, the rate at which they increment is precisely determined by omega, they will eventually spread uniformly on 0 to 2 pi. And then when they're uniformly spread on 0 to 2 pi, the contributions of modes to the density, the projection of the phase space structure into real space, will cancel more and more precisely. And the time it will take for this spreading to produce a uniform distribution on 0 to 2 pi is clearly proportional to 1 over the width of the region that you've excited. And that is what makes stellar systems dissipative. You shake a galaxy or a star cluster, it wobbles for a bit, and it settles down in a few dynamical times. And that already tells you that the Lin-Shu program for spiral structure of the 1960s never had a hope of going anywhere, because there was no possibility that spiral disks, stellar disks, would have discrete normal modes. It was a complete wild goose chase. Also, Hunter and Toomey in '69 did an elaborate analysis of warped of the vertical excitations of disks, and by hard grind and very intricate work, they persuaded us all correctly that the spectrum was continuous. But you didn't actually need to do all of that work to know the spectrum was continuous. They were discussing it. So they went into it hoping to find discrete normal modes that would explain the warp of the galaxy, etc. But there was never any hope of that working. Okay, so let's talk about Landau poles. Landau studied the initial value problem. So here is the collisionless Boltzmann equation yet again. And Landau Fourier transforms this into this, Laplace transforms it into this. Here's the Laplace transform. Integral starts at 0 and therefore has an initial condition here. So that's the Laplace transform of the potential, that's the Laplace transform of the distribution function, but this is the original distribution function at time t equals 0. Now, this equation is astonishingly similar to this equation. This is the equation of a distribution function of a normal mode. And this is the equation of the Laplace transform, or the Laplace transform of Landau's initial value problem. And clearly this maps to this. This operator is exactly the same. What it's operating on.
There is a Dirac delta that should also appear in the, first equation only has a 1 over k dot omega minus omega, but that includes the principal value plus the direct delta.
Well, we haven't done, hang on, it is just that. We haven't done any integrations yet. When we do integrations, we'll get some
Yeah, then we
deltas.
will have to-
Then I will get some deltas bearing. But for the moment, this is the equation you have for the Laplace transform. And there is this astonishing similarity. But this term, our driver, has been replaced by this initial condition term. The other crucial difference, of course, is that this thing it has to be complex. So in this equation, omega is real. In this equation, omega has to be complex. Right. If we proceed, we treat this equation in the same way that this equation, Laplace, Landau's equation, in the same way that we treated this equation. We multiply by this garbage here and integrate and so on and so forth. And then we discover that the identity minus MA, we get exactly the same stuff happening here, with A being the density coefficients associated with the perturbed potential is equal to D, where we used to have G here, D is this stuff here, right? It's the appropriately transformed Landau driving term. And so the Landau program is we solve this for A, we inverse Laplace transform to get rho, et cetera, et cetera, et cetera. Now the inverse Laplace transform is extremely tricky because, as I'm sure many people here know, because in order to obtain the Laplace transform of F, we had to assume that omega lay at a positive imaginary part. And in the inverse transforming, we need to know what this is when omega has a negative imaginary part. And there's a great deal of engineering associated with executing that, and I'm not going to bore you with going over it. At the end of the day, when you do the inverse Laplace transform, it's not exactly surprising that your final answer consists of a sum, because we're doing an integral in the complex plane, and you're going to use all this stuff about needing to know what A is for negative imaginary omega is done in order that you can close the relevant Bromwich integral contour. And then your answer comes out as a sum of contributions of e to the minus I omega t things from the poles where the poles of A omega, which are associated with m equals 1. Poles of your integrand, actually, that's not very important. Okay, now these are not the contributions from normal modes. They're the contributions of sums of normal modes. And I go back to this picture here. So this thing is I claim associated with the normal modes which lie near it on the real line. We've, through mathematical manipulation, got an answer that involves e to the minus I omega L times time, but there is no normal mode which has that frequency. And the point is that if this pole lies close to the real line, then the associated normal modes, which would be required to represent the initial condition that we put in, would be heavily dressed, and they phase mix on the time scale 1 over delta omega. And delta omega is the width of the heavily dressed part, which is essentially the same as the distance from here to here, so that the damping time is in fact 1 over omega L, over the imaginary part of omega L. Right. So I think I've talked a bit already about the mega degeneracy. I think I've said this. Yeah, but I haven't probably said this, that if you take two normal modes with the same frequency, so you've got a driving term of one of them, gk, and another driving term of another one, g primed k, right? That's a function of j, that's a different function of j. You can add them together and you've got a new function of j, g double primed of k. Their potentials can be added in the same way. Then g double primed of k phi double prime to k is another normal mode at that frequency. So normal modes of the same frequency can be added. Why are there so many normal modes? Well, to specify that normal modes need to be complete, to specify the configuration of f of x and v of a star cluster, you have to specify the density of stars at every point in six-dimensional phase space. To specify the state of a gas ball like the sun, you need to specify the density at every point in real space and the velocity at every point in real space, because you know that the velocity distribution is Gaussian. So it's Gaussian around some velocity that you can specify. So you need, much less information is required to specify the state of a gas ball than is needed to specify the state of a cluster. And that inevitably means that we have to specify the state of the cluster, we've got to specify the amplitudes of more normal modes, amplitudes and phases of more normal modes than we have to when we do this, when we do the sun, and it follows, it's then natural that there are more normal modes. All right, so an inner product on distribution function space.
So why is it natural there's an infinity? Like when do you go from finite to infinity?
From finite to infinity.
Finite number of normal modes to infinity.
Well, that's also with boundedness, I guess.
This approach, this for stellar clusters, you get an infinity.
Yeah.
For stars, you get finite.
You get a countable infinity, right?
It's countable, discrete.
Discrete.
Versus.
It's discrete versus, I mean, it's exactly. So the fact that I've got a continuous spectrum means obviously I'm going to be having the order is going to be of the continuum. In the sun, we've got, NLM, it's a countable infinity, right?
Is there an argument for why you go from one case to countable to?
Well, there's an argument why I'm in the continuum. You're asking the question, how can I know up front that the sun has a countable infinity of modes? And I guess we need to go back to our courses on Stern-Liouville problems and stuff to answer that question. I mean, it's a
Fewer degree of freedom, because as James was saying, you don't have, you haven't specified the velocities as being Gaussian, so you have this huge, all these degrees of freedom.
You could have a 6-degree freedom system, you could also have countable.
Yeah, no, I mean, I don't want to insist that it's an inevitable consequence of how much I've got to specify that the number of modes as a cardinality of the continuum. But I've argued on other grounds that the cardinality is of the continuum, and that fits perfectly, I feel like fits comfortably with the needing more information, having more.
There are examples where you have a mix of both.
Yeah.
Like Martin Weinberg had this vertical oscillations of the disk, and you had some discrete modes, and then you had a continuum.
Yeah.
But you still have the property that you can't, it's difficult to excite even those discrete modes because you always sort of bleed into the continuum.
Exactly.
So just so I can make sure I understand this properly, Steve mentions the sort of that the continuum comes from going from discrete. This, if you were doing this in like a Klementovich approach, where you actually track the individual stars in your cluster or something, that would give you a finite number of modes, one for each star, right? Because you have a specific frequency associated with that or velocity, and that gives you one resonance per star.
Exactly. I think that's fair, that if we would go back to a finite system, I mean, it's like in a crystal, I can regard a crystal as being a finite number of oscillators, and I have a finite number of modes. But when I make the abstraction of going to the continuum, which in physics, normally I think it's a very interesting philosophical question, why that is so much the natural thing to do, especially when our computers compute not in the continuum, but it is. And so I make no apology for the studying problem in the continuum. 5 minutes. Oh gosh, yeah. I need to really. Okay, so I just want to. So yes, we need to speed up a bit then. So inner product. The formula I showed you previously for the energy becomes this formula if you make F tilde F. So this is a natural inner product of the space of distribution functions. A tilde is the density coefficients associated with F tilde and correspondingly. In this inner product, you can show that the modes with different frequencies are orthogonal. This is the orthogonality relation. This inner product between the distribution functions of two normal modes, so they of course have their phi's and their g's, turns out to be this stuff, and we have this delta function, the difference in the frequencies. Okay, so that's means, for example, if you give me F, I should be able to construct F as a linear combination of normal modes, basically by choosing one normal mode for each frequency. So out of the continuum of normal modes at a given frequency, I should be able to pick out one which would have the distribution function F sub k of omega, and then add these all together for all the different frequencies, and this would cobble together this. Now it's an open problem exactly how you get that out of this, but that's what you would like to do. And that being true, the energy of the distribution function you gave me, which is not a normal mode, but of course sum of normal modes, would be this inner product. And we can show that this inner product collapses into this. It's an integral over j and a sum over k of the frequency omega k at j of an energy density given by this. So you're expressing the energy of your excitation as a sum of energies of its sum of energies of its constituent plasmons or excitations. So this is the energy density associated with one of the normal modes. Okay, applications. Antonov used normal modes implicitly in establishing the stability of ergodic systems. If I take F to be a function of E, he pointed out you can split the collisionless Boltzmann equation into two parts because the Poisson bracket is odd in V, H is even in V in this ergodic case because it starts with V squared over 2m or half mv squared. So this is even, if F is the part of the distribution function which is even in V, its rate of change must be equal to this, which is the part of the Poisson bracket which is even in V. And similarly, the odd goes like this. And then if you differentiate this equation again, we get df plus on the right-hand side, and we can show, oops, oh, bother. No, I've done millions of things. Oh, no, here we go, right. You can show, and this is just very straightforward algebra, you can show that the double derivative of f minus, the odd part of the distribution function, is minus k times f minus. So in other words, you can get the simple harmonic oscillator equation, where k is a Hermitian operator, this animal here. It looks pretty ghastly, but it is Hermitian. Now that means that the modes, because this becomes, if f minus is the f minus of a mode, this is minus omega squared times f minus, and therefore that mode is an eigenfunction of k with eigenvalue omega squared. And this is a Hermitian operator, you can show it, and therefore omega squared is positive. Oh, omega squared is real, excuse me, omega squared is real, which means that omega is either real or pure imaginary. So you never have so the modes of ergodic systems have to be stable. And any decaying mode is always paired with a growing mode.
when you can define marginal stability by setting omega equal to 0.
Yeah, that's also true, right? And orthogonality completeness follow in the same way as they do in quantum mechanics from their baby eigenfunctions of a mission operator. Okay, and we can show stability because it's possible to establish, so the energy looks like this for any excitation split into these odd parts, you can show it behaves like this. If it's a mode, then omega squared ff minus is k ff minus because k f minus is omega squared f minus. And if you work out what this thing is, it comes to this. And you put these two things together. Crucially, this has a mod omega squared in front when you work this out. And so you conclude that when omega squared is less than naught, the energy of the excitation is nothing, which makes perfect sense since it's possible that it grows. It must have no energy. Or it's equal to f minus when the mode is stable. And when the mode is stable, we can put that into here and conclude, it's this, is the energy of the mode is this. And we can show that that's this because the density associated with f minus, a minus, is nothing because this is odd and this part of the distribution function is odd in V and therefore produces no density. So this is the energy, and this energy is intrinsically positive because it is positive provided the derivative, this is the derivative of f naught with respect to energy on the bottom. So that's Antonov's stability proof. Okay, well, Chris is drawing us to a conclusion. So let me just point out two other applications. There's an application to diffusion. It's easy to show from the collisionless Boltzmann equation that the rate of evolution, this is what Chris was talking about, the rate of evolution of the unperturbed distribution function is equal to minus the divergence of a flux. And the expression for the flux is this. It's the correlation between the potential and the distribution function. And so kinetic theory, the fundamental problem is to evaluate this correlation. Normal modes enable you to evaluate this correlation via the Klemontovich distribution function. I haven't got time to take you through that. But you in this way, I reckon, with much less bother than the traditional derivation of the Leonard equation. You can get these expressions for the diffusion coefficients, which are identical with the expression for the diffusion coefficients, which you can obtain with much more aggro from Landau's approach. Something else that I think you can do is you can understand why it is when you start an n-body simulation by Poisson sampling an equilibrium distribution function in the first couple of crossing times, the large-scale fluctuations emerge in the distribution of particles, which don't emerge if you, that's what emerges if you integrate the particles in their self-consistently generated gravitational potential, and you don't get these fluctuations if you integrate the particles in the mean field gravitational potential. So there's a kind of relaxation happening there, which is not two-particle relaxation. It happens on a much shorter time scale, and I think it's a very important kind of relaxation we should be able to check. Okay, so I haven't been able to tell you as much as I hoped about the conceptual advantages of thinking about normal modes, but I hope I've whetted your appetite a little bit. So the current frontier in slow dynamics is fluctuations around equilibrium. And it's natural, I think it's blindingly obvious we should approach that through the normal modes. These are what are sometimes called Van Kampen modes, but I don't like to call them Van Kampen modes, they are the modes. And Landau poles are nothing to do with normal modes. The DFs are easy to understand physically. There's this torus on which the density is oscillating sinusoidally forever, and then sympathetic oscillations of the other stars. The spectrum comprises a continuum of real values, and that forces the dissipative nature of stellar systems. Applications I talked about too briefly about stability. I've sketched, mentioned that you can derive the diffusion coefficients using these things, and I think they help us to understand relaxation in n-body models. And I feel something that should emerge in the next few years is through thinking about the normal modes of these stellar systems, is an better understanding, because we have none really, of the large scale fluctuations that we expect in stellar systems and which should be observationally testable, for example, in globular clusters. Thanks.
Yes, we have 2 or 3 minutes of questions, and then we'll carry on the conversation at lunch. So Larry's hand was up first.
So in what we're learning in Gaia and galactic dynamics is that we see phase mixing and damping of modes and so forth in detail. And I'm just wondering how we get to, you excite the galaxy in some way and then it wraps up, and that's what we're observing, all of that. And it's not obvious how you get
it's not
the snail with this type of machinery.
The central problem, I think, is this. It's if we have a distribution function, decompose it into normal modes. So if you think about quantum mechanics, this is what you do. You take an initial wave function, you decompose it into stationary states. They are the normal modes of the thingy. You evolve and then everything lies before you, right? You can understand how they're going to interfere with each other, and through their interferences cause the system to evolve. And so that's the question. Given this, how do you derive that? And there's a sort of solution to that being offered by John Gregorian in the periodic cube, but I think the solution is actually not the right thing. I mean, it's not. Yeah. Okay.
Yoram was next.
So is it possible that Lin Shu is approximately right if you look for something like the slowest damped mode? Would that do something right?
I don't at the moment really understand. I'm struggling to understand the relationship of the dispersion relation to. I don't think I know how to answer this question. To understand the relationship of the dispersion relation, the Lin-Shu-Canalice dispersion relation to this kind of stuff, right? So what you're doing there is you're getting conditions under which you can get a local solution. And then and in the process, you discover that it can't be stationary, right? Because you have a finite group velocity. And then we start worrying about boundary conditions. And we all know in practice, the boundary conditions are basically absorbing. Something goes nonlinear and it dies. So how exactly that fits together with the normal modes? Because it must, if you write down a Lin-Shu dispersive wave, you should be able to represent that as a sum of normal modes. And that would that's what you want to be able to do in order to understand the relationship between the two formalisms. And since, as I've said, I don't know how to do that, I can't answer the question.
Should be a way to glue together a lot of local Lin-Shu things and recover this.
That's sort of, yeah, exactly. Yeah.
Last one from it.
So I guess a relatively easy way to see the emergence of the phase spiral from this is just to take the inverse Fourier transform of the Fk. So you have a Dirac delta multiplying Gk, so you will have an e to the minus ik dot omega t coming up from just that source term.
From G, you mean?
Yeah, like you have a Gk times the Dirac delta of k dot omega minus omega, right? So if you do the inverse Fourier transform, that just gives you a factor of e to the minus ik dot omega t in the time domain. So that is the phase spiral to leading order. I'm trying to answer Larry's question.
I'm not sure it's as simple as that.
And that's the naive way of thinking about the phase spiral.
Okay, let's carry on the conversation at lunch, and thanks, James, again.